Hello, everyone. Today, I want to introduce an interesting open source project, FlashMLA. This is a high-performance computing tool specifically designed to accelerate the inference of large AI models, developed by the Deepseek AI team. It's like installing a supercharger for GPUs, making AI models run faster and more efficiently. On the latest NVIDIA H800 GPU, FlashMLA has demonstrated impressive performance. When handling large amounts of data, the data transfer speed can reach 3,000 gigabytes per second, equivalent to transferring 3 terabytes of data in 1 second. In intensive computing scenarios, the computing speed can reach 580 trillion operations per second, 580 teraflops. This project primarily focuses on a deep optimization of an AI computation mechanism called multi-head linear attention, MLA. It is particularly suitable for running on the latest NVIDIA Hopper architecture GPUs. Next, let's dive into the technical details of this powerful tool together. That we will explore its features and benefits in detail. Let's first understand an important design goal of FlashMLA: optimizing variable length sequence service scenarios. What is a variable length sequence service scenario? In practical applications, such as dialogue systems, the length of each user's dialogue varies. Some may have only a few sentences of dialogue, while others may have been chatting for a long time. This variation in sequence length poses challenges for performance optimization because we need to efficiently handle these sequences of varying lengths. To solve this problem, FlashMLA employs a clever design, paged key-value cache. In this design, the size of each page is 64 tokens. Just like dividing a thick book into multiple booklets, this paging method allows us to manage GPU memory more flexibly, enabling efficient data access regardless of the sequence length. In the selection of data types, FlashMLA has adopted a pragmatic approach that IT currently supports two half-precision floating point formats, BF16, Brain Floating Point 16, and FP16, Float Point 16. Now let's take a look at the characteristics of these two formats. FP16 is a traditional 16-bit floating point format. It uses one sign bit, 5 exponent bits, and 10 mantissa bits. This format performs well when handling smaller numerical ranges, but it may encounter overflow or underflow issues when dealing with larger or smaller numbers. BF16 is a newer 16-bit floating point format, which retains the same exponent range as FP32, 8-bit exponent bits, but reduces the mantissa bits, 7 bits. This design allows BF16 to maintain a larger numerical range while reducing memory usage and computational overhead. Although BF16 has slightly lower precision than FP16, it has a larger numerical range, making it particularly useful in deep learning training. Why choose to support both formats simultaneously? This is because each has its own advantages. FP16 performs better in scenarios requiring higher precision, while BF16 is more stable in scenarios requiring handling a larger range of values. Both formats occupy only 16 bits, saving half the memory space compared to 32-bit floating point numbers at the same time. On Hopper architecture GPUs, both formats can fully utilize the hardware acceleration capabilities of tensor cores. By supporting these two formats, FlashMLA allows users to choose the most suitable data type based on specific application scenarios, achieving the best balance between precision, numerical range, memory usage, and computational efficiency. From an implementation perspective, the design of FlashMLA is very ingenious. Let's take a step-by-step look at its key components. First is the core computational kernel. The project chose CUDA C++ as the implementation language. Why choose CUDA C++? Because it can directly interact with GPU hardware, providing the greatest potential for performance optimization during the implementation process. The team adopted a clever technique, template metaprogramming. This programming approach allows us to determine data types at compile time, rather than at runtime. To draw analogy, it's like preparing perfectly matched molds for different types of parts in advance, rather than adjusting during assembly, which improves efficiency and reduces the possibility of errors. In terms of memory access optimization, Memory access in GPU programming is often a performance bottleneck. To address this issue, FlashMLA adopts a two-level caching strategy. The first level is shared memory, which is like a small warehouse on the GPU, with much faster access speed than main memory. The second level is registers, which are the fastest storage units, akin to a worker's toolbox at hand. By carefully designing the data storage and access sequence, the project successfully reduced the number of accesses to main memory. Just like workers don't have to run to a distant large warehouse every time to fetch parts, but instead keep commonly used parts close at hand, greatly improving work efficiency. In terms of computational optimization, the project focused on optimizing two key operations. Point one is the softmax operation, which is an important part of the attention mechanism and requires precision and efficiency. The other is matrix multiplication, which is the most time-consuming part of the computation. It is particularly worth mentioning that the project integrated NVIDIA's Cutlass library to fully utilize the tensor core units in the GPU. These specialized computing units act like computational accelerators, significantly improving the speed of matrix operations. Through these meticulous optimization designs, FlashMLA can unleash such powerful performance on Hopper architecture GPUs. In terms of performance testing, the project provides detailed benchmark code. The test results show that under different sequence lengths from 1024 to 32768, FlashMLA can maintain stable performance, especially under the configuration with a batch size of 128 and 128 heads. The bandwidth can reach close to 3,000 gigabytes per second at a sequence length of 8192, and it can achieve a peak performance of 580 teraflops in compute-intensive scenarios. The data shows that FlashMLA maintains excellent performance under various workloads. Of course, FlashMLA also has its usage limitations. Firstly, it only supports GPUs with the Hopper architecture, which means newer hardware devices are required. Secondly, the project requires a CUDA version of at least 12.3 and a PyTorch version of 2.0 or higher. These requirements may limit the deployment of the project on some older systems. Considering the excellent features and performance of FlashMLA, it is particularly suitable for the following types of application scenarios. First, large-scale language model inference services, which typically need to handle a large number of concurrent requests. FlashMLA's high bandwidth and computational performance can significantly improve service throughput. Second, real-time applications that need to handle variable length sequences. Thanks to its paged cache design, FlashMLA can efficiently process input sequences of different lengths. Finally, for latency-sensitive online services, through optimized memory access and computational strategies, FlashMLA can help reduce end-to-end latency. By optimizing MLA operations in these scenarios, FlashMLA not only enhances the overall performance of applications, but also helps reduce inference latency while decreasing the consumption of computational resources. This is a highly valuable option for teams that need to provide high-quality services under limited hardware resources. FlashMLA is a high-performance computing project focused on optimizing specific scenarios. Through deep optimization and meticulous engineering, it has demonstrated outstanding performance on Hopper GPUs, although there are still some usage limitations. For projects requiring high-performance MLA implementations, FlashMLA is undoubtedly a noteworthy choice. As an active open-source project, FlashMLA still has vast room for development. Possible future improvements include supporting more data types, expanding to other GPU architectures, further optimizing performance for extremely long sequence scenarios, and providing richer deployment options and integration solutions. These potential improvements will enable FlashMLA to serve a wider range of application scenarios. Finally, a reminder to everyone that the project is licensed under the MIT license, which means you're free to use and modify the code as long as you comply with the license terms. If you're interested in this project, feel free to visit the project's GitHub page for more information. Thank you for watching. See you next time.